All right, now that we've talked conceptually about what recurrence intervals are, let's talk about how we calculate them. And the first thing I want to mention here is I'm going to show you the process for calculating recurrence intervals based on a data set that's composed of historical observations. Many larger streams have these. Gauging stations are maintained by the United States Geological Service. They go out and they maintain those gauges, they monitor them, they measure discharges and compare them to different events and so forth. And then you can download this data off of the internet and do the sort of calculations that I'm going to demonstrate briefly here. However, many hydrographs many hydrograph records in the U.S. only go back 50 or 100 years. Very few gauging stations have more than 100 years worth of record. And sometimes you'll hear that a given flood was a 200 or a 500 or 1,000 year event. In those cases, hydrologists and geologists are reconstructing flood sizes based on proxy data collected by other means than direct observations. So maybe a mud deposit that's high up on a plateau next to the river that they can get a carbon-14 date on and know that, okay, 10,000 years ago the river had a flood that was able to inundate this terrace next to the stream. Or they're doing other statistical methods besides the one that we're using to calculate the basic recurrence interval for a set of historical observations like this. So just keep that in mind. This method is for historically observed data. There are other methods for extending the flood magnitude and recurrence interval estimates back in time before there were humans present systematically gauging the streams. All right. So the recurrence interval equation, it's simple. This is third grade arithmetic, no calculus here. First, recurrence interval, which is a capital R, equals the quantity n plus 1, where n is the number of years of record divided by m. So I've got a table of data here on the left side from the Root River in Houston, Minnesota. You can see the first column is the rank. So the 2007 flood was the largest flood in this river that was ever recorded, and its peak discharge on the right side of the table was 46,000 cubic feet per second. Now there were 88 years of record for this stream gauging station. So 88 years of record, 88 equals n. N is the number of years of record. So 88 plus 1 is 89. And then you divide that by m, which is the rank. In this case, it's the number one ranked flood. So it's in the table here, you see that it's 88 years of record plus 1 equals 89 divided by 1, which makes this an 89 year flood. The 1952 event, which is the second ranked, we have the same formula. It's 88 plus 1 because there's still 88 years of records in the data set. But it's the second ranked flood, so we divide by 2, so we get a 44.5 year recurrence interval. Now think about this. If you had exactly 100 years in your record, then your largest flood would be a 100-year flood. Now how much confidence would you have that that largest flood that you've observed in 100 years just happened to be the 100-year flood? What if that largest year flood was really a 500-year flood, but you just don't have 500 years worth of data to determine that quantitatively? Or what if it's been an unusually dry 100 years and you've never seen the 100-year flood? But it doesn't matter. This formula is going to make the largest flood in your data set a recurrence interval that's equal to the size of the data set plus 1 year. So in this case, the largest flood has to be an 89-year event. Now, on the other hand, let's think about down here towards the bottom of the list, we have some 5-year recurrence intervals, 4-year recurrence intervals. Now, on 88 years of record, how many times statistically should we expect to have seen about a 4-year discharge? Well, think about it. 88 divided by 4 sounds like 22 to me. So statistically speaking, we've probably seen 22 events in the last 100 last 88 years that are about roughly the size of a 4-year discharge event, a 4-year flood in this stream. So we probably have a pretty high confidence about what a 4-year flood looks like, that it's these discharges down here between 14 and 16,000 cubic feet per second. Because we've seen a lot of events that size in a data set of this duration. But we may not have as much confidence in the true recurrence interval of the largest events in our data set. Because we just haven't seen them. Now, let's say that 900 years from now, when we have 1,000 years of record in the Root River, by that time, with 1,000 years of record, we statistically have probably seen about 10 100-year floods, and we'll have a much higher confidence in what a 100-year flood really is at that point. But remember, 1,000 years from now, when we have 1,000 years of record in this data set, we're going to have the very largest flood that's ever been observed over that 1,000 years will by default be mathematically the 1,000-year flood. But we're going to have low confidence in that. It won't be till maybe 5,000 or 10,000 years of record that we have a good feel for what that 1,000-year event is. And this is a good example. One of the reading assignments for this module talks about the 2007 flooding in the Root River near Houston, and I'll give you a little spoiler and the answer to one of the questions that you're supposed to consider and think about is that this 2007 flood, you can see it's quite a bit larger than the second biggest flood. We went from the fourth, third, and second biggest floods were 31, 34, and 37,000. We're 25% larger here for this biggest flood. And some other methodologies for calculating the recurrence interval of this 2007 flood would suggest that it's really a flood on the order of several hundred, maybe even 500-year magnitude. So some nuances there. So how do we plot these recurrence intervals? So we take the data from the previous table that we calculated, and normally we use a semi-log graph. Semi-log means that our x-axis, where we're plotting recurrence intervals, is a log scale starting at 1 year, 1.1, 1.3, going up to 10, and then 20, 30, 40, 50, and up to 100. But we have a linear scale on our y-axis, which is discharge in this case. So let's think about the data for the Root River. We'd plot all those points from the table in the previous slide, and maybe the first point we plot was this 1,500 cubic feet per second discharge, which was a 10-year recurrence interval. We plot the rest of the data, and remember there'd be 88 data points. I'm not going to show them all, but we plot all the data, and then we can put a trend line through that data, best fit trend line, and we can use that trend line to make predictions. So when we have 88 data points along this line, and if we have a good fit, if the line is a good fit for all 88 data points, then we can extrapolate for areas where along that line where we don't have floods of that size and our magnitude. So let's just assume that this is a very good data set, even though it's only three data points. We haven't seen maybe a 20-year flood, but we could estimate that the 20-year flood, the 20-year recurrence interval flood, would be about 17 or 1,800 cubic feet per second. Now here's the actual plot for the Root River, the data set shown in the table in the earlier slide. The red boxes are all 88 floods observed, peak annual discharge floods observed in the Root River. You can see that with our R squared here, we have a 0.98, which is really good. 1 would be perfect. So we have a really good fit to this data set. And we can see where our highest flood plots, and it's right about 100 years. So I updated the data table on that earlier slide from the USGS data repository before I made this graph, and now there's not just 88 years of record, we're nearing 100 years of record for the Root River now since that table was created that I showed on the slide. So at this point, because we have nearly 100 years of record, that 2007 flood is nearly considered a 100-year flood. But what I would say is look carefully at the gap there. You can see the gaps are increasing between these various recurrence interval events that are up here at our higher end, but there's a bigger gap than we might predict. I really think that this 2007 flood, based on other data sets that I'm aware of, is more than a 100-year event. But because we have this, because we have this best fit line through here, we can extrapolate both what a 10-year flood looks like, and maybe even a 100, 200, 300, a 500-year flood would be about 60,000 cubic feet per second. That's assuming this 2007 is really what's plotted here, which it probably isn't. So you've got to be really careful when you're extrapolating and forecasting out beyond the duration of your data set what a 500-year flood would look like, or a 1,000-year. There are methods to do that we're not discussing. Okay, so who cares about all this? About recurrence intervals and all these things? Well, I know you've heard these things in the news. Today's not the first day you've ever heard of a 100-year flood. But these are used for a lot of things, including determining flood zone boundaries, which govern insurance rates, the suitability of sites for various uses, planning and zoning decisions, and so forth. And building in the floodplain can be really expensive in terms of insuring the house. So this is a diagram produced by the Louisiana State University Extension. Of course, in Louisiana with the Mississippi River and so forth, they have a lot of flooding issues and lots of communities where flood insurance is very important. And a house built above the 100-year floodplain, just above the 100-year floodplain, may have an insurance premium that's about $1,400 per year. So over the course of a decade, that's about $14,000 in premiums. Now, if that flood is just a little lower and built within the 100-year floodplain, so has a likelihood 1 in 100 years or a 1% probability in any given year of being inundated like these houses are in the picture here on the right, then those flood insurance premiums jump way up, $9,500 per year. Over 10 years, that's $95,000. Now, even if this was a really nice house that cost $250,000, $300,000, $400,000, let's say that it's a $300,000 house. Now, over a 30-year mortgage for that house, you're going to pay nearly $300,000 more just for the insurance. So that just doesn't make any economic sense to build in the 100-year floodplain. People do it all the time, but if you're going to insure your investment, which you're required to do if you have a mortgage on your house, you may pay as much for the insurance as you do for the actual house. So a lot of people really care about this. All right, so as we wrap this lecture up, I'm going to leave some parting questions for you, some things to think about as you do the reading assignments associated with this lecture on flooding. Okay, why is the terminology of a 100-year flood confusing to most people, specifically non-hydrologists? You should understand what recurrence intervals are and how to express them. That was the main point of this lecture. And you should understand the assumptions behind recurrence interval statistics and how those assumptions affect the usefulness of RI calculations. Let's say that we can't assume that stationarity is a good assumption. If stationarity is an invalid assumption, how does that affect our designation of the 100-year floodplain in various communities? Remembering that 100-year floodplain is determining whether your flood insurance premium is something like $1,500 or $9,500 per year. So think about what effect does that assumption of stationarity and the assumption that our watersheds aren't changing have on calculating these recurrence intervals, particularly in light of our changing climate. All right, with that, we'll end this lecture. And I encourage you to go back and review the questions that I posed at various points in this lecture. And with that, we'll see you the next time.